Also guten Morgen allerseits. Herzlich willkommen zur PC4 Vorlesung. Wir befinden uns in der dritten Woche und nur zur Erinnerung, wir haben ja ein Inhaltsverzeichnis für diese Vorlesung. Wir sind immer noch ganz am Anfang, also in dem großen Kapitel Theoreme und Postulate. Wir hatten zuerst die Einleitung. Excuse me, we speak in English. So first the introduction. The second chapter is theorems and postulates. And within this first chapter, we also had a little introduction here. Just formalizing things, and then we entered the subchapter on heroes. Now we are nearly done with the heroes. Are there any questions regarding material we have covered last week or the week before, for that matter? If there are, please interrupt me or paste them in the chat. I'll be proceeding now, and what we had written down last week was at the end was a theorem, the first theorem, which stated that not only the expectation values, but also the eigenvalues of heroes are real. So if your expectation value of a hero is real, then so this means a hero, Hermitian operator, then also the eigenvalue must be real. So that was theorem one. And the second theorem which we mentioned at the end is that the eigenfunctions of heroes of non-degenerate eigenfunctions, these eigenfunctions are orthogonal. So you have some eigenfunction. You would get the eigenvalue and the eigenfunction back, and then any inner product between such eigenfunctions gives you the Kronecker delta function. Okay. So we can briefly demonstrate this point. So let's say like this. Easy to demonstrate. Okay. So suppose you have a hero B So B acts on some eigenfunction f with eigenvalue s and f, and another function g with eigenvalue t and f, right? And so, oh, sorry, g. These two eigenfunctions have to be linearly independent, of course, which means that's of course, otherwise you would get just a multiple of each other's eigenvalues. So that would be considered a trivial case. So suppose these eigenfunctions are linearly independent, right? Now we have to see if they are truly orthogonal. So this is the question. Okay. So let's take the expectation value f b g, and that is the same as saying g b f complex conjugate. And now we know that if B acts on G, we should get our eigenvalue T. Right. And similarly, on your right-hand side, B acts on F, and so you get your eigenvalue S. Okay. This means that T F G is on your left-hand side, and on your right-hand side you have S G F. And sorry. And now we know that this is S F G. Okay. And thanks to the second theorem, we also know that this eigenvalue must be real, right? And so for this reason, you can now compare these two, and if you do that, you can say that T minus S, you factor out the inner product, must be equal to 0. Okay. Now, how can this be the case? Well, this is a product of two terms, right? And T minus S cannot be 0 because we consider only non-degenerate eigenfunctions, right? Since we only consider non-degenerate eigenfunctions for theorem 3. Right. And because of that, this term must be equal to 0. Okay. Now, of course, you can ask, but what about degenerate eigenfunctions, right? And in fact, it's possible to also do that. You would have to expand your eigenfunctions in a different basis to deal with this. Now, basically, you would have to orthogonalize your basis function space. You can show that it also works, right? It's also possible to show that Theorem 3 works in degenerate cases. And what one uses here are linear combinations of eigenfunctions in the space of the other degenerate eigenfunctions. So you need a linear combination of eigenfunction in linear combinations of eigenfunctions. This is an eigenfunction with the same eigenvalue. Now, I'd like to skip the proof in this lecture to save us time, and it's not so important for future cases when we restrict ourselves to the non-degenerate problems. You should just keep in mind that you can always, if you encounter the degenerate problem, you can always change into a linear combination in those degenerate eigenfunctions, and then typically all the theorems still hold. Right? So that's the take-home message. All right. So this is what I wanted to tell you in this second subchapter, and I'd like, unless there are any questions, I don't see any so far. I'd like to proceed now to the next subchapter, which revolves into around the next theory. So my apologies, I'm a bit. No, I'm sorry. I have to correct this. So our first theorem is the one on the eigenvalues, and that's the one we use here. It should have corrected me here. And we are working on theorem 2 here, so this should be theorem 2. Okay. So I'd like to go to Theorem 3 now, which is part of our next subchapter. Okay. So we are in theorems and postulates. This was 2.1, 2.2, and now I'd like to go to 2.3, and this is about series expansion. Okay. So we have this this theorem 1 on the eigenvalues, and then we have this theorem 2 on our eigenfunctions, right? So these theorems, this is something you want to distill. You should prepare yourself a cardboard or something where you note them nicely down, and you should memorize them. They also form an important part of the general education as a chemist. When people ask you about basic quantum mechanics, right, you should be knowing about such theorems, right? So suppose your colleague from high school who decided to study mathematics chats you up after university and is asking you about the kind of functions you are talking about when you're dealing with your electrons in your chemical problems. You should then be able to reproduce these theorems. Right? So theorem 3 is part of the series expansion. And the theorem states that you can form a complete set of eigenfunctions for any hero. So any hero. Now remember, the heroes are the operators we care about, right? So we are talking about the entire mathematical universe, and we are basically in using these theorems, we are narrowing it down to that mathematics that matters for chemistry. Okay, so this is what this is, right? Now here's the theorem. Any hero has a complete set of eigenfunctions, right? So let's call them GI, and there's n of them, okay? So this is a fairly general statement, and you will see in a minute why it matters to have a complete set. But first, we should note that in general, this theorem actually is a postulate, which means we cannot really prove it, okay? So it's a postulate in general. But you can prove it for specific cases. Now, a mathematician would insert only here, right? Now, we, as chemists, we would strike that through because our specific, the mathematician would say it has been shown only for chemical application, right? But that's all we care about, okay? So for us, that's not only. And also, I mean, so one has to be careful when reading the mathematical statements, right? Typically, they are much more rigorous, right? In the sense that it becomes, yeah, you could nearly argue it becomes dogmatic, that even a negligible probability, let's say, for tunneling through a macroscopic object, let's say, for a mathematician, that probability is still non-zero, right? And so it's worthwhile talking about. And that is, of course, mathematically, that's very true, right? We want to understand if something is exactly zero or not. But for any chemical application, negligible probabilities are negligible, and we shouldn't be talking about it. It would be a waste of chemical resources, right? So you have to be very careful. The language can be too forgiving here, and one has to consider the right phrasing in such cases. So that's why I strike through this only. Mathematically, the only is justified. Chemically, it's not. Now, here's another thing. So you could also say that this theorem is worth less because it's only a postulate in general. Now, you have to keep in mind that there are quite important postulates in the rigorous sciences. Another one would be the axioms of Newtonian mechanics, okay? Or Einstein postulated that the speed of light is a constant, right? So these are postulates. You cannot prove them. Right? They have been inferred. You can infer them by observing nature, and then you arrive at that conclusion that in all likelihood these postulates are true. But that is, of course, that should render us all modest, right, in terms of what science really means. But of course, these postulates are so powerful because over time it turned out they've never been proven wrong. Right? There's not a single incident where they have been violated. And so that, of course, strengthens our confidence in them. But strictly speaking, it's still a mere correlation, if you wish, right? So that's why we distinguish this, and that's why we call them postulates. Okay. All right. Now, why does it matter a set of functions is complete? It turns out, and maybe you know this already, it turns out, and this was shown in 1807, it was shown an amazing thing. I'm not going to show it to you, right? But it was shown that if you have a complete set, right, then you can expand any kind, right? So any of those functions which we decided we would limit ourselves to, right? So differentiable, continuous functions, any such function you can expand in this set of eigenfunctions. Let's put it like this kind, right? So continuous, differentiable, finite, and so on. state function. Now I add state here because we want to describe the state of the electrons, right? So that's why we add state here. Right? So any state function can be expanded exactly, so without approximation, in set of complete eigenfunctions, or in a complete set of functions, right? So let me so this statement should help you to appreciate the importance of the third theory. Okay, this means that it's something amazing, right? That the heroes, the operators we care about, they have eigenfunctions, and so we since these operators are something we care about, right? These eigenvalues are things we measure, and the expectation values are things we measure. This is something we care about, and the space of these eigenfunctions they have, this space, this set of eigenfunctions can be used as a basis to describe any state function, right? So it's the cool thing about this is it doesn't matter which of these operators you actually pick. It doesn't have to be a complicated operator to get a nice set of eigenfunctions, right? So you're free in picking your favorite operator with the favorite eigenfunctions to expand something horribly complicated, such as the electronic wave function of some distorted geometry, in a very simple set of functions, right? So let me write this still in math symbols. So any function, let's say psi, can be written as a bunch, a sum over these eigenfunctions we have here, and some coefficients. Okay. So that's what Fourier showed, where this is the complete set, right? Eigenfunctions of some hero. Yeah. So you know examples of such eigenfunctions. Think about something like the eigenfunctions which you get from the quantum harmonic oscillator. Okay, quantum harmonic oscillator has some eigenfunctions. These are Hermite polynomials multiplied with some exponential function. Okay, so it looks you have this the mass, the oscillator strength, pi h bar square root over 2 to the n factorial square root times, so there's a prefactor m omega x squared That's your Gaussian exponential, which takes the form of a Gaussian, times this Hermite polynomial, which depends on n, right, the index for your function, which we associate then to the quantum number, right? So you can think about this. This is your solution for the nth level, and this is your nth eigenfunction, right? And this is the spectrum of your harmonic oscillator. You know, the energy is equidistant in this quadratic potential. And in these solutions, right, you probably know them. They look, then you get the different number of nodes and so on, right? So you know this picture, I presume. This was a bad drawing, but this could be the third level. So you know these pictures, right? And so in this set of eigenfunctions, you can now describe any. So those are the eigenfunctions of your Hamiltonian operator, which is a Hermitian operator. And so they form a complete set with which you could describe any function. Could be a sum. You start from 0 up to infinity, an of these psi n, your harmonic oscillator solutions. Now that's a very nice way, right? So then you don't we like this. You have now a concrete example in what kind of functions you could expand your electronic distribution in space, right? You can put these basis functions, right? So you could, for instance, put these psi, right? Your Gaussians, they are centered somewhere in space. You could imagine that this could be a 3D coordinate, and you measure its deviation from some reference point, right, in your Gaussian here, your x squared, right? Or your x. Let's just put x here. Let x be this distance, right? And you put your R0 on some atom, right? On every atom you can have an R0. So then you sum, you do the same for every atom. So and then all of a sudden you have your basis functions in which you can expand the electrons, right? So that's how you mathematically, how you can describe electrons in space, okay? And it's mathematically, it's completely legal, right? We build this on top of these theories, right? So I'm trying to convey here the idea that we have a very rigorous and physically well-founded framework on which we can base chemistry, right? All right. You can also think about, so do this at home. Look at the eigenfunctions of your particle in the box. Okay. So same thing. You can could you do this with the hydrogen atom? You know the solutions of the hydrogen atom, I presume. It's getting complicated because in the hydrogen atom case, you reach at some point in your spectrum, you reach the continuum. And for the continuum, we don't know the analytical expression of these eigenfunctions. So in principle, yes, but unfortunately we are too ignorant, right? But now you can see the cool thing, right? To expand the electron density of, let's say, the hydrogen molecule, you don't need to know all the eigenfunctions of the hydrogen atom. You can get away with the eigenfunctions of the particle in the box, right? If you account for the right dimensionality of them. And those we know very well, right? So that's the power of theorem 3, right? We can just change to another basis. We can pick the basis that's most convenient to us, right? That's very cool. Right? That's so nice. Now, there's a nice example. Let's say example 1, example 2, example 3. So for hydrogen atom, we do not know the analytical form in the continuum. So this means we do not know the complete set, right? But that's our fault, right? I mean, here you in the theorem you say, the theorem says you need to know these solutions, of course. Right? It doesn't say anything about how to get the eigenfunctions, right? That's the problem of solving the eigenvalue equation. Separate problem, right? Theorem 3 supposes you did that already. Now, if you failed, like in the case of the hydrogen for the continuum states, then you will be in bad shape for theorem 3, of course. Now, here is another really nice case. You should absolutely know about it. And that's the momentum operator. What about those eigenfunctions? What if we took the eigenfunctions of the momentum operator and we did a series expansion? What would that look like? It's a hero, right? So Px, the hero, obviously, so should be applied. The theorem should be applicable. It's minus I h bar differential operator, right? Okay, that's our hero. Now, does anybody know what we call that series expansion in the eigenfunctions of the momentum operator? Nobody knows? Okay. So probably it will blow your mind. What is the eigenvalue problem? Px times applied to our eigenfunction, let's call it gk, spits out the eigenvalue, let's call it k, gk. Right. So we use k is the number as well as the index as well as the eigen. So that's the eigenvalue equation. And the solution, the generic solution for any level k is that you do this ansatz where you use your function, an exponential I k x over h bar. Okay, and k can now run from minus infinity to plus infinity. Okay. So just a complex exponential function, very straightforward. And when you differentiate it with respect to x, you get this this prefactor, the minus IH bar back, and you want this k as the eigenvalue, right? So it's quite intuitive why this should be the solution. Now, what about theorem 3? So let's build this expansion. We have some psi of x. We write it as a sum minus infinity to plus infinity, ak gk. Okay. Now, if we write that out, then I now put the explicit form in and of the eigenfunction, and I put the index k. I put this as an argument for your a, okay, for your prefactor, your coefficient. And you can do this if you change from something like an index towards something continuous. And so in the continuous limit, right, the summation symbol simply becomes the integral. And so you integrate from minus infinity to plus infinity over k. Now, if you look at this right-hand term, at least some of you should identify this as a Fourier transform. This is also known as Fourier transform, which is, of course, at the heart of all your NMR measurements. Okay. So what NMR does is expand things in the eigenfunctions of the quantum momentum operator. Didn't you know? All right. There's one more remark I'd like to make on this theorem number 3, and then we go into the break. So there's a there's a common practice. So very frequent operation we like to do, which is that we multiply, we call it, we multiply from the left and we integrate. Now, this it's a jargon thing, right? Which is why I put it in, and I phrase it like this here. Normally when you multiply, it doesn't matter if you multiply from left or right. But what we mean here is that you multiply from left with the complex conjugate, right? So this is doing this operation, JK, right? And you can think of it like an operator, right? And that's why I like to write my integrals like this, right? So now we are integrating everything that's on the right-hand side, right? And so that you can apply this to an equation, right? When you have, actually, you should have seen this already in other courses. And we will see this also later in the perturbation theory. We make use of this, that we come from the left with the complex conjugate and we integrate. Okay, so why am I saying this here? Let's look at what happens if you do this operation to your CS expansion. So let's operate, right? And yeah, so you're now applying, it's like an integral operator, right? So we operate now d tau, integral over d tau, gk star on your phi, okay? So what happens if you do that? Right? So let's insert our expansion, right? We have a sum over all our eigenfunctions. They have coefficients in front of them for the linear combination, for your CS expansions. These coefficients are just numbers, so you can always pull them in front of the integral, right? And so our integral goes through the summation symbol, right? So they can go through each other, and you integrate over tau, right? But for each AI, AI is just a number, so the integral goes through, and then you're left with our gk, of course. So that's an eigenfunction now in the space, in our x space, or whatever is relevant for our phi. And you're left, of course, with your original eigenfunction. And what do you have here? What you see here is nothing else than your inner product of two eigenfunctions. And they must be orthogonal, right? So the only term that survives in the sum must be the A coefficient, right? That belongs to the eigenfunction which you used for your operation, with which you operate, right? So this is the sum AI Kronecker IK, and that gets you the coefficient of your kth eigenfunction, right? So if you, and we will see this again in the interpretation of quantum mechanics according to Born, we will see this again, that this is how you can get any of these coefficients. You can extract them from the entire series, right? So if you're interested only in this one prefactor, then all you have to do is multiply the whole series with the corresponding eigenfunction, and out it comes, right? Now we call that whole thing is also known as projection. Right? So this you also say AK is projected out. Right? In German is herausprojizieren, okay? Or you can also call this the projector operator, okay? So this is the projector operator. You do two things, right? You multiply with your complex conjugate eigenfunction, of your interested index, and you integrate to exploit the orthogonality. All right, that was the remark I still wanted to make. Now, let's have a little break. It's 5 minutes past, so let's reconvene at 11:20, please.
Sorry, I just want to ask what you meant with particle in the box, and then you said like the same.
Oh,
and what did you mean there?
Oh, so you can write the same. You can also, you know, the eigenfunctions of the particle in the box, right? You can write again any function. So this is above you have the eigenfunctions of the harmonic oscillator, and you can also write, let's call them Fn of particle in the box function, right? I
see. Okay, thank you.
So in that sense, of course, these eigenfunctions are different. Yes. Thank you. All right, let's take a break, and I see you back at 11:20. Okay, let's continue with the lecture, unless there are any questions. I'd like to now finish off this subchapter on the third theorem. And there's still one final remark I should make on the notation of the brass and cats in combination with this these projectors of the projection. Okay, so just to clarify, sometimes it can happen to you that you encounter this kind of expression where you say, I have this function and it looks like this. Okay. And so what is this, right? Now you have the tools to understand this. So suppose F is our expansion in our complete set of eigenfunctions. Okay. And now we know from this projection, we know what this coefficient AI, what this is. Okay. So we can substitute this. Okay. Substitute AI is the same as your integral d tau gi f. Okay. So we can insert this here. Okay. Now that is the same notation wise as just writing this. Oh, sorry. And that is the same as, now we just change here the position, GIF, right? And now we introduce the following notation. We say define F to be the same as F, and define GI to be GI. Then this whole thing becomes F equals sum over I GI, GI F. Okay. And now you still say you replace your, we had that in the first introduction of our second chapter, that if only the index matters, you can just put the index just as well, right? And that leads you back to what we originally described, right? So this is also called known as the projector. So it's basically that you you inserted, it's a substitution of this projection trick into your series expansion, right, to describe for your coefficients. Okay. So if there are no questions, we will now move to the next subsection, and that's going to be on eigenfunctions. Okay. So we are talking now on subsection 2.4, eigenfunctions. So this subsection revolves around theorem number 4. And again, I'll just start out with the theorem, and then we will demonstrate it. Theorem number 4. Okay. So theorem number 4 is about what can we know about the eigenfunctions of heroes, right? And apart from them being useful as basis functions, right, there's another really cool thing, and that is theorem 4. And it says that if you have two heroes, and you write down their commutator, you should know. And if the commutator is 0, right, so that is identical to saying the order with which you operate doesn't matter. If that is the case, then and only then there is a joint complete set of eigenfunctions. So their eigenfunctions are the same. So that's crazy, right? Imagine you have two different operators. They could have no or hardly any recognizable relation to each other at all. If they commute, they will have the same eigenfunctions. Right? So the solutions to the eigenvalue problem, the functions are the same. So this is really extremely powerful, right? you can probably grasp by now that it can be really tricky to find the eigenfunctions for an operator. So if you are posed now with a new operator and you're asked to get the eigenfunction, the first thing you should do, rather than starting actually working on the problem, first thing you should do is check if that new operator commutes with any of the operators you know already. Right? Because if it does, the problem is solved. Now, this is something we can easily show. Suppose A operating on this eigenfunction spits out eigenvalue AI GI, and B operating on that same eigenfunction gets its own eigenvalue and that eigenfunction back. So consider this. And we expand now our function in a complete set of these eigenfunctions. Right. So this was Theorem 3. So now we would have to show is a B when operating on this F indeed 0. Okay. So remember, when you deal with commutators, you have to, if you just look at them without any functions, it's a bit abstract. It's always easier if you actually use some function, right? So that's what we're going to do. Let's write that. Here, and so now we use our expansion. And now I write it more explicitly. Okay. So not yet obvious that that must be 0, but let's start operating now. So we operate first the left-hand term. So B operates on GI, and that should spit out your BI. Okay. And then A operates on GI, and that spits out your AI, right? Okay, now these eigenvalues are just numbers, so we can pull them in front here, BI, A minus AI, B, GI, and now I'll repeat the exercise, and I get BI, AI minus AI, BI, GI. Right? And that thing here must be 0, right? So if they have indeed these the same eigenfunctions, right? You basically can factor them out from the commutator, and then the order of multiplication of the eigenvalues doesn't matter, and so it must be 0. Right? If they had not the same eigenfunctions, you couldn't factor them out like this. Right? Now, there's a caveat. the set has to be complete. So that means they must commute for all eigenfunctions. For all eigenfunctions, okay? If it's just for one eigenfunction, that's not sufficient, right? So that means this corresponds to commuting only for subset is insufficient. So here's an example for that. For example, the angular momentum operators Lz and Lx, they do not commute in general, even though both do have the joint eigenfunction, the spherical harmonic in its lowest state. Okay. All right. So it must also be complete, right? The complete set just one joint eigenfunction does not mean yet that your operators commute, so you really have to look at all eigenfunctions. Now, if they commute, right, you can use the same eigenfunctions over and over again. Right? So this is how it's useful. Even very useful. So if AB is 0, then consider a solution, then you operate with B and since they commute, that's the same as this, right? And so that must be the same as this. So this here is a new eigenfunction of A. Okay. So this means GI and EGI must be linearly dependent, since BGI equals BIGI, right? So this is AI, BI, GI. And then your eigenvalue of the operator B merely becomes a multiplicative constant. Now, this is not a trivial thing, because that multiplicative constant is different for every eigenfunction. Right? So as you go through the spectrum, this multiplication, it's like a nonlinear change of the entire spectrum. All right. Are there any questions so far? That doesn't seem to be the case. So let's proceed with one more remark here. What happens with degenerate functions? What about degenerate eigenfunctions? So it's similar to what I said in the end. You can also consider this degenerate case and expand again in the space of degenerate eigenfunctions. So suppose AI has n degeneracies. Okay, means there are n eigenfunctions which all spit out the same eigenvalue AI. Okay, so what happens? A operating on BGI, again, this is the eigenfunction now, gives you this AI BGI. And now we can do this expansion in this set. So you say BG expansion in, and now I call this K, in these n degenerate eigenfunctions. Set of degenerate linearly, they must be linearly independent and this means your A, GK and AI, GK for all K. So this is then also here one can show that all these degenerate eigenfunctions are also eigenfunctions of B. We will not provide this proof here, but suffice it to say that it's possible to show this. So this theorem 4 is also powerful in general in that sense. So it covers that scenario as well that you are talking about, degenerate eigenfunctions. Okay, are there any questions?
Yes, I don't think I understood what you meant in the above section. GI and BGI must be linearly dependent.
So what you have here, right? This BI prefactor here, this eigenvalue, right? It just corresponds to and you compare this and you put it in here, right? And you see that so your A can operate on G, right? And you get your AI times G. And now you insert your B in between, and then you get your AI times BI, right? So your eigenvalue AI just got increased by a factor BI.
I see, okay.
Right? So that's just a multiplication, right?
Mm-hmm.
It's
okay.
Yeah, so thank you for asking. It's when you phrase it, right, it might sound more complicated than what it really is, right? It's just that your eigenvalue can be a multiple. Okay. And that multiplication factor, you get that from the B. Okay. All right, now I'd like to go to Theorem 5. And we now consider that you have a hero A that commutes with the hero B. Actually, B doesn't have to be a hero. B just has to be linear. But A has two eigenfunctions. And if A commutes with B, then it turns out that the expectation value for B will be 0. So,
I'm sorry, you just wrote Theorem 4 again. I think you meant 5.
Oh, I'm sorry. Yes, absolutely right. Thank you. So let's write that out. The expectation value of B is 0 for A GI AI GI. So GI being eigenfunctions of hero A and for B being linear, it's these three conditions. And for A and B commuting. So this is important, of course, right? So this means that you could not measure B if it commutes with A and happens to be linear, right? It's zero. Yeah. So in some sense, it's also it renders your hero special, right? So this theorem is about the operators, right? So in your operator space, you cannot come with whatever operator you wish, right? So the question, which maybe if you recall in the introduction of quantum mechanics, where do the operators come from? We use the correspondence principle. But that's a non-trivial thing, right? This is not, by no means is this obvious, right? And it's so important that you pick the right operator. So this theorem tells you that actually you cannot pick any operator you wish, right? And there will be many choices, right? If they are linear and they commute with your already existing operator, let's say the Hamiltonian, then you will not get an expectation value in that eigenfunction space, right? All right, and recall, so the operators correspond. These expectation values are supposed to be observables, right? So in quantum mechanics, you cannot observe whatever, right? We are not at that liberty, right? All right, so this is also, we can easily show this, right? Easy to show, right? So we write that expectation value, and now since B commutes with A, right? So because of theorem 4, we can get the eigenvalue. And so we can write it like this. And this, of course, is the Kronecker delta. So our orthogonality. Right? So this cross term, right, must be zero, right? So if here we assume that I not equals J, right? So this must be zero. Right? So the whole thing is zero since the I and J are orthogonal to each other, which was our theorem number 2. Again, also in this case, we can make this work for degenerate functions. Okay, we are approaching 12 o'clock. I have the next subsection that we could start. Are there any questions so far? No? So the next subsection will be about parity. And, sorry, my pen is dying on me here. Now, this will lead up to Theorem 6, but I should say a word or two on the basic forces of nature. And there are four forces. And that's some of this is still being researched, and we can discuss about it. But most physicists agree on this, and so you can roughly think about things in terms of gravitation, in terms of weak forces, in terms of electromagnetic forces, electromagnetism, and strong forces. Okay. Now, let me give you some examples. What are the particles? That experience these forces. Gravitation acts on all particles, okay? Also on your molecules. So don't underestimate gravitation. It's definitely a part of the entire picture. The weak forces act on left-handed fermions. The electromagnetic forces act on anything charged. And the strong forces act on quarks, hadrons, gluons, that sort of stuff. So bound states include galaxies, planets, stars, right? For these fermions, we don't really know. we have electrons and atoms, and these are the nuclear forces, so nuclei, right, kept together like this. And now in relative strengths, we set the nuclei and the electrons, this we set to 1, right? Suppose the ionization potential of hydrogen or something like this. Then the nuclear energy is roughly 20 times more energy, right, than chemical energies. These weak fermions, this is on the order of 10 million times weaker than chemistry. And gravitation is on the order of 10 to the minus 36. So it's really hard to find strong effect. Now, these weak forces, they violate the parity of your electrons. And this is something we want to talk about. It means, this violation basically means that enantiomers in chemistry are, strictly speaking, not energetically degenerate. Okay. There's a difference due to the handiness of space. And this difference is 10 million times smaller. But if you have 10 to the 23 molecules, right, you can imagine that a small number in a Boltzmann sense could kick in and shift your balance. All right, we'll talk about that more tomorrow. It's after 12 o'clock. I'd like to thank you for your attention, and I hope you enjoyed today's lecture, and I'll see you tomorrow.
All right, have a question.
Sure.
You mentioned something about expansion, but I don't think I called it correctly, what you said.
Expansion?
Yeah, you mentioned it twice, I think, that you expanded something, I think an operator, and 2 operators, in fact.
Are you referring to the Fourier expansion?
Yeah, I think it might have been that.
So today we touched upon expansion multiple times on the CS expansion. Maybe you can pinpoint the exact place and we talk about it tomorrow. Is that okay?
Yeah, that's fine. Thank you.
All right. Thank you.
Goodbye.
Bye-bye.